Hello. Okay. So, what do we do if we don't have a large sample and we'd still like to make some kind of estimate? Well, if we can assume that the sample is normal, which may be possible due to frequency data from the past, histograms and the like, and we see that maybe it is reasonable that it's normal, then maybe we go ahead with this type of model here and we can still make some progress even though n is not big enough to warrant assuming the estimator is normal. Now you're thinking maybe, well, look what you did. You just said each one of these is normal. So of course, like y bar is normal. So what did you do? You just replaced one sort of estimate with another. And while that's true, there is another thing here, which is that with large sample, when we used s squared to estimate sigma squared, we have a lot better chance to get this close. With a small sample, we need to we have another approach. Okay, so we're going to use a different distribution, which actually will be close. Okay, will be closer. But we still, in a way, we really haven't gained much ground. We still have to make some assumptions here. We still have to make this assumption. Maybe good enough. Okay, so because yi is normal then, so let's say we're thinking we want to estimate mu. So y bar will be, again, our estimator for mu. And of course, y bar is normal too. It's normal with mean mu and variance sigma squared over n. And also we have y bar minus mu, if I want to sort of standardize it like this, over the variance, which would the square root of the variance, which would be sigma over square root of n. This is going to be standard normal now. Under this assumption, this is exactly true, and it doesn't matter how big or how small n is. Okay, right. Okay, also, and, right, n minus 1 s squared over sigma squared is chi-squared with n minus 1 degrees of freedom. And these are independent. S squared and y bar are independent. Doesn't matter how big n is, always true if the population is normal like this. And remember, in Dennis Wackerly, this is theorem 7.3, the big one that we proved for n equals 2, and will prove later in this week or next week for n in general. Okay, so then I can make something t-distributed. So recall if z and say, let's call it x, are independent, and z is standard normal, and x is chi-squared with, say, new degrees of freedom, then z divided by the square root of x over nu is t-distributed with new degrees. Okay, that's the definition of the t-distribution, or a definition. And we've seen the PDF for this. We've derived this density, and it is symmetric and converges to the standard normal distribution as nu goes to infinity. But for smaller nu, it has heavier tails than the standard normal. You might remember this. So there's the standard normal. There's t nu. Okay. So using this, we can, out of this, we can build a t random variable. So we set t equal to y bar, using exactly what's up there, mu over sigma over square root of n. And we divide this by the square root of our chi-squared divided by its degrees of freedom. So n minus 1 s squared over sigma squared over n minus 1. This has a t distribution then with n minus 1 degrees of freedom. Let me simplify this. And you see the sigmas cancel. The true sigma cancels with this one, so that's good. We're left with only one unknown parameter in our expression here. So I have y bar minus mu. These n minus 1s cancel. And this goes in the denominator here. So this just gets replaced with s over square root of n. And this is t with how many degrees of freedom? Not n. It comes from here, right? It comes from this chi-squared variable, so n minus 1 degrees of freedom. All right, so since only, let's write this, since only mu is unknown, we can form a confidence interval for it based on t. Yes. Okay, similar to the standard normal, the book uses this upper tail notation. So if I have something that is t, it actually doesn't put the degrees of freedom. It assumes you know what it is from because you're working on the problem. But let's just say I have something here that's t with new degrees of freedom, and it will give me this will be called t, say alpha over 2, if this is to be alpha over 2 here, which is the case if we want this middle part here to be 1 minus alpha, and this would be minus t alpha over 2. In R, we could put the new in, so we would have t alpha over 2 in R is just equal to q quantile of the t distribution. And don't forget, now I need to specify the probability to the left of this point, which would be 1 minus alpha over 2. And now I can put the degrees of freedom in and be more precise about what this value is. Okay, well, we're there then, I think. If I want a confidence interval for mu, then we know that if we want, suppose we want 1 minus alpha to be equal to the probability that. So again, this is like using a standard normal, knowing that its probability it's between 2 and minus 2 is about 0.95. So so if we want 1 minus alpha to be the probability that t is less than t alpha over 2, or q, to be more specific, qt 1 minus alpha over 2 n minus 1 for this problem, then yeah, so if I'm specifying this to be the confidence level, I really need to find this, right? And this is equal to this. Okay, so we have, maybe I should have said we have, and we use this to get the confidence interval we want for mu. Okay, so then this is equal to the probability that, let's go to our abbreviation here, T alpha over 2 is less than T, which is just Y bar minus mu over S over the square root of N. And now we can just solve for mu here. So this is equal to the probability that, well, I multiply here. So I have Y bar minus S over square root of N, T alpha over 2 less than mu less than Y bar plus S over square root of N, T alpha over 2. Okay, yes. So there's your confidence interval. Here's your confidence limits are your center is at Y bar and your radius is this, right? And as a probability statement, this is exact and true. You are saying the probability that these random numbers, this, and this, enclosed mu is 1 minus alpha. Okay, so let's do a little example here for this problem. So suppose we have 10, so say n equals 10. That's actually not that small, so you could maybe use a normal, a large sample estimator, a large sample pivot. You maybe could do that, but you'll see it's actually different for this one. So I actually wrote all the data out here. So let's say y, we could write it like a vector and just list it like this. I wrote them in order, of course. They don't, no, I didn't write them in order. 5, 12, 4, 7. So these are the hunting days for the licensed hunters, the number of days they actually hunted. From my sample, I had 10, and suppose made up, totally made up, and I get Y bar 12.7. I had S squared was 177.1. I have S 13.3, and suppose we want 1 minus alpha equal to 0.95. Now, we just did the lecture on selecting sample size. I'm not able to both bound the interval and set the confidence level with a fixed n, right? So this is different. I have a fixed n, and I could specify the bound or the confidence level, and it's usually more important to specify the confidence interval. It's usually more helpful, I should say. So we'll specify the confidence level at 0.95 and compute our radius, basically. We already know this is going to be the estimate for the number of days a licensed hunter hunts. And we're going to now find a confidence interval that will say I'm 95% sure it's between, well, we already did find it in random terms where it's 95% sure that it's between these two. Now we'll find an actual, the confidence interval sample that comes from this particular sample. Okay. All right. Okay. So what do we want? We want we need T alpha over 2. So we have T 0.025. This is just Q 0.975, right? And N minus 1 is 9. And if I do this, I get 2.262. So one thing to notice is when we did this for the, sorry, this should be QT. When we did this for the standard normal, we got 1.65, I think. So you see, you have to go farther out to enclose 95% of the probability under the T with 9 degrees of freedom. And you have to go out to 2.26 instead of 1.65. So it's the tails, this is known as the tails in the T distribution, are heavier than in the standard normal. Okay, so there we are. And now we're essentially ready. We have all these numbers, right? So we have then the 95% confidence limits for this data are 12.7 plus or minus. Now I just put this in, right? So I need S over the square root of N. So I have 13.3 over the square root of 10 times 2.262. And let's see, this gives me, you can see it's going to be about 10. It's 9.52. So like between about 22, right, and 3. So what do we say? What does this mean? Let's just get in the practice of saying this, what it means, to make sure we keep understanding what it means. So what this means is the interval 3.18 up to 22.2 was computed in a way so that this could go in parentheses under assumption in particular that the yi's were normal and independent. So this was computed in a way so under this assumption, 95% of such intervals contain mu. Okay, so we're 95% sure it's between 3 and 22 roughly. We do not expect the mean number of days a hunter hunts to be more than 22 or to be fewer than 3. Okay, we got another part for this coming up, but we will stop this one here.